Oh, can you hear me? Hello, hello.
Yep.
Good. All right. Okay. Let's see who's connected. How many people are we expecting today? You're muted.
Counting us, it should be 18, I believe.
Oh, okay. Let's give a couple minutes, wait a little bit. All right. Nobody likes the Monday morning spot?
Yep, they haven't had the 8 a.m. lab yet, so.
The good news is I was able to get some XPS data, not depth profile, that takes a long time. But the machine was, we had some issue with our XPS system, but it was pretty much up and running Friday afternoon. So I was able to run a couple samples. So yeah, I mean, I'll explain a little bit how XPS works, and it'd be good to compare to the EDS we will get. Because I put the same samples I put in the XPS. I put those two samples in the machine right now. So we'll see how it compares, and maybe we can do some flip cross-sectioning. I mean, we'll see. I mean, it's an investigation, right? So we can bounce ideas and decide what we want to do. I mean, I kind of have an idea of what I was going to do, but we can change that anytime, of course. I'll just wait an extra minute, and then we'll get started. I'll just set up the screen sharing. Okay. All right, well, let's get started. Again, this is going to be recorded, so we can, I mean, I will share that as soon as I can, and then you can always email me questions later or stop by. I mean, any of those are good. All right, so what I want to do today is, well, first briefly, pretty much rapidly go over what we've done last time as far as EDS goes, and just get back to that track of thoughts that we have, you know, going from the cross section to the side, and then I did some FIB and XPS, so we'll just go through that, and then I have a couple samples in there. The other two that you gave me, the side ones. So there's one that is, I think that was 100% in potassium, and one that was 5% silver, I guess in sodium nitrate. So those two I looked at in the XPS, and I have those in the machine. Okay, and then I always have that second mount. It's ready to go from last week if we want to look at a line scan on the cross section. All right, so here we go. Let me start sharing the EDS screen. All right, you should be able to see the EDS interface. So again, stop me at any time if something is not clear. I just want to make sure we're all on the same page as we go through the lab today. So here's what we did last week. So what we did first, for EDS, was we put that puck that was you know, cut with the saw and then polished, or yeah, not super high polished, but you know, good enough to see clearly the interface between here the embedding material and the glass rod, and we went to the 5% silver in potassium nitrate, I think. And what we did first, we did a few EDS points or regions, not exactly at the edge, but just kind of, you know, about 1 millimeter in, or like 0.5 millimeter in, and tried to see if we could see silver, and we couldn't. So remember, that's an EDS spectrum. It shows you the energy of the X-rays that we are capturing coming back from the sample. And if you put over there where silver should be, there wasn't anything clear on this one. Went to a few spots, another one a little closer to the surface, maybe 0.5 millimeter. Again, we couldn't see silver. So we did a few of those closer to the surface. Again, nothing visible really as far as silver goes. And then we switched to doing line scan. So I zoomed in and really tried to capture the first, 100, 150 microns within the sample. And we did a few of those. Where's the silver? So calcium, of course, at the transition, you start seeing a lot of carbon, a lot of oxygen inside. I mean, oxygen, silicon, of course, it's glass, and sodium. But as far as the silver, it was pretty much just background noise. So we did a few line scans, again, at the surface. Couldn't really see silver close to the surface. Again, background noise. Where's the silver here? Yeah, again, look at the percentage. It's just really noise. So our thought process was, okay, maybe when it's embedded and we grind and we polish, it had a tendency to damage the first few microns, or I mean potentially more. So what we did is we put a similar sample. I think it was the same. Yeah, 5%. The silver salt in potassium nitrate. Yeah, that's the one. So we looked at it on the side this time. So that's the surface of the sample. And with a spectrum, let me go back to that other option. Just a spectrum at the surface, EDS spectrum, and then we could see clearly silver. Okay. So what that indicates to me is that, yes, there is silver at the surface of the sample. I'm not exactly sure how deep it goes. I know that when I do EDS on a material, depending on the accelerating voltage, so the electron energy that we use to create the signal, we're thinking about maybe the first micron being probed, something about like this. So if we see silver, that means that there's silver in the first micron. It could be the first 20 microns. It could be the first micron. I'm not sure. We couldn't see on those line scan in the physical cross-section when we were grinding the sample. So that kind of indicates to me that it's only the first, maybe 10 microns or even maybe shallower that has silver in it, and maybe that was damaged in the physical process of cutting and grinding. So what I did after the class was that same sample, this one, I did what we were starting to talk about at the end of the class, is I did a FIB cross-section. Okay, so let me prepare some, let's see if I have some images I can share. I think I started to talk about this at the end of the class, but I want to show that again so that we have this in mind. So I will share just my browser. Seeing from the chat, which sample is this? Well, the first one we did, the only one really we really studied in depth last week was on Mount 2. I think that was the green one. So it was yellow. So that was the exchange 5% silver nitrate in potassium nitrate. So what I did on it is a FIB cross section. So that's really, put that a little bigger. That's what I did, where you tilt your sample and you have a focused ion beam in the machine and you start cutting perpendicular to your surface. And then the SEM can image that cross section, and not just image, but also generate X-rays. So you can do EDS on the cross section. Okay. So my thought was to do a line scan on the cross section, and because you don't involve physical, cutting and grinding, maybe you can capture the first few microns a little better. So let me open that those results. All right. So I think this one was good. So I went quite deep. So if you can see what's happening here, this is the initial surface of the rod, And I protected the surface a little bit by depositing some material in the chamber. We'll come back to that maybe if we do a free cross section today. And then I exposed the cross section. So this is just perpendicular to the surface. Okay, and then I did a line scan from the top. It's a carbon pad protection rectangle here, but then you can see the whole profile here. And I could see silver. Let me see the line scan. Here we go. So if I go, I think it's at the bottom. Yeah, in silver here, you could start to see, a significant amount of silver, and then it's just slowly decaying. So that tells me, the technique worked pretty well. Where I'm a little confused is that if you look at the scale, we're talking about tens of microns, all right? So question is did we lose that much in the embedding, cutting, and polishing, grinding that we really disturb the first 20, 30 microns? That seems a little brutal to me, but I guess that's what the numbers are showing. So that was the good news, that with the flip cross section, you can, you could see something here. Do you have any questions? No? So we can bounce ideas, of course. What I was planning on doing today is I have the two other samples that you gave me last week. Not the one embedded, but the glass rods that are fully exposed. I can see the surface. I was going to first do some EDS at the surface. So one of them is ion exchange in 100% potassium nitrate. And let's see in EDS if we can see the potassium and compare with XPS data. So I did XPS. Before I present that, I explain how XPS works, another technique. And the other sample I've looked at and we have in the chamber now, I haven't looked at it in ADS, but I did XPS on, is another 5% silver salt in sodium nitrate. So I want to see if I can see the silver in EDS here. I think so, because I see it was yellow. So far it's been a good indicator of being able to see silver in EDS, but we'll see. So is that a good plan? Should we do that? Yeah? I remind you that those are your samples. I'm trying to do something interesting here, but if you want to do something specific, you need to tell me. All right, let's go to the SEM view. Oh, I have to go back here. All right, you should be able to see the interface of the microscope now. I'm going to turn the beam on. And the first thing I'm going to do is take a top view of the sample, so I can navigate. Okay. So this on the left is the one that, I'm not sure you can see that. Yes. So this on the left here is the one that we looked at last week, the one we just discussed the results about. And those two we haven't looked so far. So I just labeled them yellow and clear because that's difficult to see in those images. So the one at the top here is the 100% potassium nitrate, the clear one. And this one is 5% silver, yellow one. Now you can see some, let me put that a little bigger on the screen. You can see some change in colors here. So remember what we talked about last week about needing the sample to be conductive or somewhat conductive for electron microscopy, because we send electrons, they have to go somewhere. So glass is really not a friendly sample. So what I did is I used some paint, some conductive carbon paint here. And I also sputter coated some regions. I masked the center, but I sputter coated some regions with, I used a gold palladium alloy. So I have maybe 10 or 15 nanometers of metallic coating that hopefully goes all around the sample and meets the graphite coating, so that when I image, hopefully the electrons can go to that film and escape the sample, so we don't have too much trouble. But this at the center is the sample without any coating. So if we do EDS on those, we're not going to have any gold palladium from the coating. Okay. So I think I'm going to go to this one first. I'm interested in this one, the clear one. Okay. You can see the edge here. If I'm in the coated region, I can go there. I don't have any problem. The system is behaving well. I can get an image without struggling. As soon as I get to the glass side, you see all those weird contrast happening, because that's uncoated. But it's not too bad with the proximity to the coated region. All right. So maybe we go somewhere here. And I want to focus a little bit. Position my sample so that I'm in the right position for EDS analysis. All right, that's decent. And now I'm going to share the EDS computer view. So let me reopen the other project. I want to make sure I save everything in the same project. Yeah, this one. And what I'm going to do is make a new specimen. And this one I'm going to call, I think you had it labeled 100K. So I'm going to use the same thing. All right. And before I forget, I'm going to insert the EDS detector because it's not in right now. If I go back in here, you should start seeing it coming from the top here, closer to the sample. Here we go. All right. Again, it's optimized for the sample surface being at 4 millimeters. So that's why I moved the sample up close to that marker. And I want to do the same settings I did last week so that it matches. So last week, what we did, and I can check the details of that spectrum, we use an accelerating voltage of 10 kilovolts. Okay, so remember, we have to have the energy of the incident electrons high enough that it can excite the X-rays we're trying to see, right? So silver has some X-rays at about 3 kiloelectron volts. So we want the accelerating voltage to be about 2.5 times more. So that's why 10 kV was a good choice. So we're going to do the same thing, which means I'm going to go back to the microscope and go from 2 to 10 here. I'm going to bump that up a little bit too, so that we can get a spectrum in, not in 2 hours, but in a few seconds. You see how increasing the energy, the sample doesn't like it, of course. I mean, I'm pushing electrons inside the material. It doesn't know what to do with it, but it's okay. We can still do the analysis. So, all right, go back to the other computer. I'm not going to do a land scan. I just want to do a point on the side, just see if we can see potassium, I guess. So here we go. I'm going to grab the image first. Yep, I can do that. That's fine. And then I want to acquire a spectrum. That's a little dark. Here we go. Do something like this. There it is. So the spectrum is growing, and I can identify what's in it. So oxygen, can have some carbon. That's going to be a silicon. So that's the glass, of course. I can see potassium. All right, it's good. Sodium, magnesium, aluminum could be also from the surroundings, but and no silver. I mean, there should be any silver here. It hasn't really been involved at all. So no silver. See what tells me. Yeah, calcium. It thinks maybe it sees silver. See, we're starting to be in the noise. So I'm not sure if there's some residue here of things, but it has a little something. Hard to tell because you have lots of peak overlaps at that with so many samples. So many elements, sorry. Yeah, actually, it's not really sure it has silver because it's showing in red, so it's just failing statistical analysis. All right. Now I want to have a look at the other one. The yellow one. Let's see here. So same thing, I just acquire the image and then make a box and see what we get from this. So here I think we're going to have much more significant signal that shows that you have silver. Yeah, silver in it. Yeah, you can see the several peaks. It's going to be your calcium, and you have sodium, magnesium. No potassium. Yeah, no potassium. It's showing a lump aluminum. That's interesting. Probably in the glass.
Is that little peak between silver and calcium? Is that where potassium would be?
Yeah, but that's a silver peak.
Oh, okay, that's silver peak. Okay.
Potassium. Yeah, I mean, it is an overlap, but the fact that we don't really see here, you know, if you ask the system to use the data to create a number, it will. But see, when it's showing in red, it's just statistically, it's just not meaningful. So you can push the system, but
I didn't see the extra silver peak there.
Yeah.
So.
And actually, so I've done those two samples in XPS. So I want to show the XPS data and see that's where actually it's good to have XPS because it's more sensitive and it's very surface sensitive. So here it would pretty much give you an answer to, do you think you have potassium or not? So I don't think so, I'm not sure, but that's where we can talk about XPS. So let's do that. So far nothing crazy, except maybe that we might see some silver in that one. But it's not super clear, right? But you shouldn't have used any silver salt or anything in that one, right? The 100K.
Yeah, there shouldn't have been any noticeable amounts.
Yeah. So yep. Okay, we'll see if this is just background noise that's been like really amplified. I mean, we don't really see the second peak at all. It could be, I mean, I'm not going to get into the details of false EDS peaks, but it could be a little bit of like two aluminum peaks together creating that peak. We'll see what XPS said. All right, so what I want to do now is stop sharing this and start sharing again the browser. Here we go. So what I want to show is XPS, not this one. Spectroscopy. Here we go. So XPS is another technique that we have available at the center. XPS is X-ray photoelectron spectroscopy, and this technique, the main one of the main benefits of this technique is surface sensitivity. So I was talking earlier about EDS, depending on the energy of your incident electrons, probing the first half micron to a few microns, okay? Which for many cases is considered the surface, right? A few microns is very, very thin. But many times that's, I mean, in surface science, that's considered bulk sample. I mean, a few microns is gigantic. So XPS probes the first 10 nanometers. So it's not, you know, it's a completely different magnitude here that we're talking about. And remember where EDS that we've been doing so far, the way it works is we send electrons and we capture the X-rays coming back from the sample. In XPS, you send X-rays and you capture electrons coming out of the sample. So it's kind of like the reverse thing. Of course, when you send X-rays to the sample, those X-rays are gonna penetrate quite deep into the sample. I mean, you know that when you think about X-ray, you think about, you know, seeing through things. So of course, the X-rays are gonna penetrate quite a bit and generate electrons in the material. But those electrons that it's going to extract have such a low energy that they are going to be reabsorbed right away unless they are very, very close to the surface. And that's why you can have that really great surface sensitivity. So I think this is a good image that I've used in the past. Let me see if I can get a high resolution of this. Yeah. So here's the idea about XPS. Again, you send X-rays. That X-ray is going to knock an electron out of the atom. So it's called photoelectron because it's a photon that created that electron. And again, this has such a low energy that only the one close to the surface can be captured. So if you see on the right here, if you have a substrate and several films, for example, the X-rays are going to penetrate very deep, as I was saying, but only the photoelectrons close to the surface are going to be able to travel. So you might not be able to see film B or A, depending on the thicknesses, and you're not going to be able to see the substrate. So that's very interesting here. Because, for example, what we've been doing so far in EDS, when we do a spot at the surface, even if you see silver, if the silver is only in the first couple hundred nanometers, you are really underestimating how much silver there is, for example, because a lot of your signal is coming from what's below, which might not have any silver. So when the EDS is just, you know, telling you a composition, it's telling you an average composition of the whole volume that's been probed, which might artificially really decrease the silver content because it's just very thin. Now, XPS is going to be so close to the surface that it's going to be able to really show you what's at the top of the surface. So the way it works, again, that's the physics of it. The instrument is looking like this, just like an XRD, X-ray diffraction system. X-rays are made by shooting electrons to an anode, a material, and then those are the X-rays that we focus and use and send to the sample. If you start seeing this, that really also puts in perspective what we do when we do EDS. Is when we do EDS, we do this part. Instead of using an anode, like in XPS or XRD, where you have like a really pure copper or aluminum plate, that in EDS, that would be your sample here, and you get all of the X-rays. In XPS or XRD, you have a pure material, copper or aluminum, and you try to select only one very fine X-ray energy and use that as your incident signal to analyze your sample. So anyway, we shoot the X-rays to the sample, get the photoelectrons, they go through an analyzer, and then you can detect what's coming out of it. So let me share. Where is it on the desktop? Here we go. So I'm going to stop sharing this, and I'm going to share. Okay, so let's go first to the potassium sample. Where is it? Here we go. Okay. So I couldn't really do good quantification. Was really pressed with time, but I did run some scans at the surface of the sample. What you can see is not like EDS where you have the whole spectrum growing. You really have to scan every element with a range of energies. So that's the 100K sample, okay? And what you can see is that you see, I mean, the usual suspects, right, for glass, I mean, silicon oxide. You see a lot of carbon because the surface is so surface sensitive that any contamination or residue at the surface will be showing clearly. And what you could see in this one is you could see potassium, but we also saw the silver, right? Which is a little strange, right? Because, I mean, when we go to, I mean, we did see a little bit of something in the EDS, right? You know, a few minutes ago, and we didn't know if it was real, but I do see some silver at the surface of that 100K sample. So I'm not sure if it was like bath contamination or like a little bit of a residue or something. I'm not sure. I mean, it was clear, but I see a little bit of silver, and I definitely see some potassium, just like the EDS showed. You notice that I named this sample potassium sample with no edge, okay? So that's the surface, the first few nanometers, 10, 15 nanometers of the surface. But as I was just mentioning, XPS is so surface sensitive that you capture a lot of surface contamination. So what you often do is that you clean the surface a little bit. So in our system, we can use an argon ion beam and just raster the argon ion beam at the surface to try and erode, you know, mill the sample a little bit to get rid of that surface contamination. And then you see what's below. So I run a second time the sample, this time with, after 30 seconds of etching it. Sorry, let me make sure I'm sharing that. There we go. So same sample after etching it 30 seconds. So it doesn't tell me a depth. It's kind of, you know, moving the beam on it. If you want to know exactly how much you remove, you would have to pretty much put some standards and run, and then look at how deep, you know, you go. So I mean, it takes a little while, and it's, I mean, it part of a big study, you do that. But when it's just having a quick answer, you don't really have time to do that. But what I can tell you is that 30 seconds in our machine, you're not removing microns. I'm talking about removing, you know, 10, 30, 50 nanometers maybe. So what you can see here after the same sample, after I clean the surface a little bit, is that the silver peaks are, you know, not this one, mostly gone. So that's what we had before, that silver that we don't really know how it got here. After cleaning, those two large peaks, they're pretty much gone. So that tells me that the silver was maybe just some residue at the surface or something. But what you can see is that the potassium signal that was, you know, it was there, but a little faint, but we could still see it. Now we clearly see it very nice. So that would tend to indicate that, yeah, there was some silver residue at the surface. I'm not sure if it was cross-contamination or something when rinsing things, but it goes away as soon as you get, you know, a few tenths of nanometers below the surface, and then you are clearly into the potassium signal. Okay. So I did the same thing on the other sample, the silver sample, the yellow sample. And I've done before and after etching in the XPS system. So same idea here. I mean, we can try and compare what we see here with XPS, EDS. So again, you see silicon, oxygen. I mean, that's normal, right? You clearly see the silver. So obviously there is silver. We saw it in EDS too. We cannot see potassium. So no potassium here. And after cleaning the surface, we see the silver even cleaner. So, you know, we don't have as much carbon at the surface. You see how much carbon I had before cleaning. And see, we're talking about 10 to the power 4. After cleaning, it's just much, you know, it's an order of magnitude lower. So it's cleaning up the carbon, hydrocarbon contamination at the surface, and the silver signal becomes cleaner too. See, it was a little noisy, but then you really get into the sample, and then you clearly see the silver, and you get no potassium. Okay. So the question we had in EDS, which was, you know, do we see potassium in that sample, or because the potassium peak is very close to the silver one. Well, that the XPS tells me that you have no potassium. Even at the top surface, you get no potassium in that sample, just silver. Expected? Not? I guess you. I can hear you.
I'll let them take that.
Okay. Well, I'm not hearing anyone talking, but just keep your thoughts. But I think at some point you'll have to write that down, right, in a report or something. I don't know. But just think about those observations and what it means.
So that is kind of interesting. I told them a little bit of the background of we have had trouble finding potassium in EDS. So
yeah.
The fact that at least part of that is confirmed by XPS, like in this sample, this 5% silver in sodium, right? Or sorry, 5% silver in potassium sample. No
potassium.
Yeah, no potassium.
What I mean, you have made a lot of samples, right? I mean, I have a lot of mounts, there's a lot of samples. I would say don't think, I'm talking to everybody, especially you, the students, don't think that this session is necessarily it's the last live session, I guess, but don't think about it as the last opportunity to test samples. I'm more than ready and open to analyze others. If you come to me and you say, just check 1, 2, or 3 other samples with EDS or XPS on the side with the fib cross section, just think about a plan that would maybe answer some of the questions you might have. I mean, it's an investigation, right? I mean, you have to go back to the drawing board and say, okay, this confirms what my suspicions were, or maybe I have another question mark, and to get the answer, I need the XPS for surface sensitivity, or maybe I need EDS depth, on a cross section. So you have to come up with those, and don't hesitate. I mean, I have all the samples. There's a lot of them. If you have a few that you want me to run, can certainly do that. So we'll also remind that, the soda lime glass, I mean, there are some stuff in there. And the techniques we are using are sensitive, especially XPS. So you always want to keep that in mind, One thing we haven't done, I think, is a baseline, which I could do. But yeah, I would say you should suggest some other samples maybe to run, some conditions, that sort of things.
I just wanted to confirm one thing about the samples. So I'm just looking at my lab notebook that I took for the samples that I gave you. So I gave you one labeled 100K.
That's correct. Yeah, that's right.
And then 1,5 silver potassium.
That's the one we looked at last week. Yeah.
Okay. And then 5 silver sodium.
That's right.
Okay.
Yeah, and that's the 5 silver sodium that we just talked, last. That doesn't show potassium.
Okay. So the one that we just looked at on XPS was never exposed to potassium. If my logic's correct there.
Well, it seems to indicate, the result indicates that, yes. The funny thing is the 100K shouldn't have been exposed to silver, right?
Correct.
But it did show some silver at the surface.
Yeah. I think your assumption of possible contamination might be the case. We do have to reuse vessels. We tend to get most of the stuff out, but there could always be a little residual.
Yeah, and I mean, XPS is very surface sensitive. I mean, you can see examples online of people just barely touching the surface they want to analyze with brand new gloves, very clean gloves, and that just throws the whole thing aside, I mean, the whole composition, I mean, you start seeing all the elements of the gloves and everything. It's that surface sensitive. So if you have a residue of 100 nanometers of silver, or even 50 nanometers, that's gigantic for XPS. Actually, let's try something. Let me share the EDS screen again and go to that potassium sample, right? This one. So in that 100K, we saw a little bit of silver, and XPS confirmed that. So that was an analysis at 10 kilovolts in the EDS. I want to see if we see it, if I bump up the voltage here. Let's see. I go much higher. What do we see? All right, EDS computer, and just grab the image, make a box, and see what's in there. Okay, carbon, oxygen, silicon, yeah, silicon, sodium, magnesium. Almost no silver. Compared to this one, we had a little bump here. Now we still do have a little bit, but I think it's not as much. Yeah, it shows not as much. I hope you're guessing what I was trying to do or what I'm doing. What I'm doing is that I bumped up the energy of the electrons that I'm sending to the sample, so they penetrate deeper. So all of a sudden, the volume that we are analyzing is a little bigger, okay? And because the silver is mostly at the surface, as shown by the XPS, I want to get an idea of if we have the silver signal decrease in EDS. If it does decrease, and it did, that means the silver is really close to the surface. And as you start probing deeper into the material, and I'm not talking tens of microns, I'm talking going from half a micron to a micron, you start to see the silver quantity kind of decrease. So that tells me that it's just residue at the surface. It's not, a few monolayers thin. I would call it significant, maybe, but it is there, and it's not super deep, but it is there. Let me go back to the, yeah. So no edge, we clearly had silver, and after edge, we had not a lot, but we still had maybe a little bit, but not a lot. See this peak, 368, a little bit, not much. So anyway, close to the surface, but that's about it. All right. What's our plan now? Do we want to do, so we have a few options, right? We have an hour. Do we want to do fib cross-sectioning and then the line scan on that fib cross-section on one of the sample? Or do we want to put the mount that was mechanically cut and polished and do some line scans on it? For example, trying to get an idea of the potassium in that 100K maybe. Well, I'm not sure if that 100K is in there. Oh no, I'm not sure we have it in the mount. I guess, do you have an expectation on that 100K, like how deep the potassium goes? It seems that it's not just at the top surface, it can be pretty deep. So we could do a fib cross section to see that. I don't think I have it in the mount too. I don't think I do. I'm listening to you all.
So you said you're looking at mount 2?
Mount 2 have, mount 2 I have 3 samples. Didn't you say the red one became kind of yellowish?
So we have 3 of them there.
Yeah.
Red, green, blue. The red is the 100% potassium.
I don't think I can see the red dot anymore, but yeah, I have this sample. So the question is, I guess we should do both, right? I think we should put that sample, the red, in the mount 2, the 100% potassium, and do the land scan on the physically, made cross section. If there's a lot of potassium and it goes very deep, maybe hundreds of microns, then hopefully we see that in the cross section, right? If it's the same deal as last week and we don't really see the potassium, we can always put back the side of the sample, the one we looked at a few moments ago, and do a field cross section and see if it leads to the same conclusion we did last week. That sound like a plan? Sounds like a plan to me. All right, I'm going to take the EDS detector out, and I have to vent and replace the sample, so I'm going to put my gloves on and I can share the screen so that you see what's going on. So I'm going to turn the beam off. You see how this is paused here? That's because when we do EDS, it pauses this automatically. Remember, X-rays are photons, and the live view I have in the chamber is, made by infrared light, so also photons, and that just completely overwhelms the EDS detector, so it pauses automatically. On new system, if you have a very old system, if you work on something like that in the future, make sure you always pause whatever live view you may have, because all your results are going to be crazy. So let me vent and put that mount 2. I'm going to try keeping that that sample in. Yeah, I think I can have both in the machine, so that would cut down on pumping time. We only vent now and pump now. All right, should we just take a 10-minute break since it's going to be venting, pumping? So it's 9:50, right? And just meet back at 10. Then we have the full hour to continue. Yeah?
Works for me.
All right, let's do that. Let's meet again at 10. And I'm pausing the recording now. Starting. Okay, I should be recording again. All right, back to it. So what I did was so I kept those 2. So this is the one we're going to study, I guess. And I went to the equivalent on the puck, right? I mean, I don't know if it's exactly the same rod, but it's the same idea, right? So ion exchange in 100% potassium nitrate. That's the red one, I think, this one. All right, so I'm here. See the green cross? That's where the stage is. I'm going to turn the beam on. We don't need that much. I'm going to bring that back to 10 so that it matches what we've done in the past. Here we go. Oh, we're on the edge, actually. So let's go to, maybe here it's a little cleaner. And I'm going to insert the detector. So I don't know if I mentioned that, but I retracted the EDS detector before I vented in the machine. It's a good habit to take not to have the EDS detector inserted. Many new generation EDS detectors are windowless, and that sudden change in pressure from that high vacuum and letting nitrogen in, nitrogen gas to vent can make some damage. So even if you have older style detector that can handle the change in pressure, I wouldn't do it. I wouldn't take the risk. Those detectors are expensive, so I retracted the detector and I just inserted it back in. All right, so I'm going to, so I call this one a puck cross-section. So click start to grab the image, and just like we did with the other one, you can see the boundary here with the puck, and that's the rod. So I'm just going to make a box right now, just see what's in there first. Wow, doesn't see the potassium here, right? Let's just give it a second. Oh, maybe we do now. Do you have a quick question?
I can ask it later. It's helpful in sending the guitar thing in.
Okay, yeah, I'll be done in 1 hour.
Cool.
Thanks. So we might see a little bit of potassium here, right? Really not much, but just a tiny peak. So maybe let's try to get a little closer to the surface. Maybe over here. Now we see it's coming slowly. It's going to be a calcium here. Let's give it a second. Nothing super significant. Again, if we compare to what we did earlier on the side of it, oops. That's how much we had, right? So we should see some more than that, I'm hoping, right? So maybe just do the land scan. Maybe it's not that deep. Maybe we really damage everything when we cut. That's really surprising, but so let's switch here to a land scan, and I'm going to go to the edge here. I mean, if you look at the scale bar, I mean, I say I'm close to the surface, but I'm still like a few hundred microns, from the surface. So that's actually really significant. Ooh, the charging effects are not good. So I'm going to go a little slower. Maybe you can get something a little better. Okay. And make a line from the outside in. Let's see what we see first. Maybe we'll zoom in after that. Let's put the potassium in. Yeah. Let's give it a minute. Right now, it's really just kind of random background noise. So that line is quite long, I mean, 400 microns. So maybe we're looking at something that's just right here. So we'll zoom in, do a line scan here, and then we can always do the FIB cross section as we talked about. Yeah, it's hard to tell anything really from that. Let's zoom in. Okay, so I'm going to zoom here. Maybe I need to zoom in a little more. I think we see a little big, so let's see that. Okay, I'm showing the right screen. I was checking. So the edge is supposed to be close to that. We start to see something here. With charging, it might have moved a little bit, so that might be an issue too. I think what's happening is also that not the sample is moving, but the I need to check that. Yeah, okay. Let me show you what I see here. Depending on how fast or slow I scan, because of charging effects, the surface of the sample becomes negatively charged, so it's repelling the incident electrons. So they don't land where they are supposed to land. They land a little bit to the side of the region that are really charged. And you end up, I mean, this results in the image moving. Okay, the sample is not moving, the image is moving. It doesn't matter when you do your line scan, if the sample is moving, then you see when I started, you started to see a region that was a little higher in potassium. And as I waited, it kind of like pretty much was starting to widen and disappear. And you didn't see, but as soon as I stopped, I looked at the image and it actually was shifting. So what we can try to do is try to use some drift correction techniques. Someone try to do this. Once you get into those problems, it's a little tricky. So let's see if we can do that. If it's responsive to this technique. Let's do something like that. Uh-oh. Okay. Let me go back here. I think this didn't work. All right. Stay with me, a little glitch in the software. There we go. I can try also here to be closer to, well, it's not that bad. Try to be closer to a region that doesn't charge as much. And they very well might not be any good region, but we can try maybe here. Yeah, you see charging effects. Still, let's try this region. Oof. I think it's moving a little too much, but let's see. That's too calcium. Interesting. The other region was more promising. Maybe I'll go back to the other spots. So maybe, yeah, depending, I guess, do you see all here, that little gap that we see here? That's between the rod and the embedding material. So it also depends on when you cut and when you polish, where the blade or where the blade exits, and also when you grind, where the grinding paper exits. You know, it's different from when it enters the sample. So that could lead to different things. I mean, there is a real peak here, but I think things with the charging effects have probably moved. Actually, I'll show you. This is the original image, and when I'll stop the EDS, it might just move. Yeah, see, it went lower all of a sudden. So I do think we have something, but we're talking about pretty shallow, maybe 10, 20 microns. How does it look here, the gap, disturbed area? Yeah, see? Try to see if we can find a region that's a little more fused, let's say. Maybe here on this opposite side is better. Yeah, let's try right here. Oops, sorry, I'm showing you the right screen. It's clearly moving, but it's okay. Let's try this. It is showing calcium. That's good. It's a good sign. Yeah. So hopefully it doesn't drift too much. But you see, at the beginning, you can see here that we're talking about maybe 6 microns, something like that. Yeah, I think maybe the signal is moving a little bit, but that's not very deep. It disappears quite fast. Yeah, that's my drift correction. That's just going crazy. Actually be better without drift correction, so we can try that. Actually, let's do it back here. It's really concentrated within a few microns. But you do see the potassium peak. So yeah, this is just a fake thing, but let's see, it's gone already. So we're talking again, yeah, it's about the same thing, 6 microns. If you start here, 9 to 15, that's kind of the idea. So let's try to capture this with the fib, right? Make a cross section and see if we can get a clear thing. We can try that. I'm going to stop this, and I'm going to retract the EDS because I don't want it inserted when I do my fib. All right, so back to this one. And I'm going to go to the sample right here. Okay. And I'm actually going to go to the coded region. Because when you do the fib, you don't want to have drift. And we might still have some movement, so we'll see how manageable that is. Here we go. Okay, so I'm going to go, come on, right here. Change the settings a little bit so we can see better, hopefully. There we go. All right. Bring the sample higher in the chamber. We want everything to be about 4 millimeters, just like for EDS. That's the surface of the glass. Good. Now the first thing I'm going to do is insert a tube. You see it coming from this side. And what I want to do is deposit a little bit of a protective layer at the surface of the sample. I'll probably use carbon. So I have to use those settings, low voltage to stay close to the surface and high current. Hopefully it doesn't drift. We'll see. Maybe I'll put even more. I'm going to make a box here, right here. Oops. All right, I'm not going to put that much. So here's what I'm doing. Well, it takes a few minutes every time to do those steps. So I want to make sure I explain, but I want to get those steps started. So what I'm doing now, well, the goal is to cut perpendicular to this surface, right? We want to see the cross section of this. So to do this, we're going to use the focused ion beam that's on the machine. To cut, the way it works is that we turn on the focused ion beam and then we make some boxes where we want to cut, and then the ion beam will move there and remove the material, just mill it away. But before I want to start using the focused ion beam, I actually want to protect the surface a little bit, because as soon as I use the focused ion beam to get an image, just to position where I want to do the cuts, as soon as I image the sample, I'm going to destroy the sample. I'm going to start modifying and mill the surface of the sample. So if you're trying to study something that's very close to the surface, of course, you don't want to mill it before you even have the chance to do a proper cross section. So usually when you make a focused ion beam cross section, you first protect the surface a little bit with a material. So you can, outside the machine, deposit a micron of something, a metal or something, or you can do it inside the system, and that's what I'm doing now. Right now, I'm depositing some carbon at the surface of the sample. So I'm just going to put a little bit using the electron beam. So the fib is not involved just yet, just the electron beam, GSEM. And this is just to coat the surface with a sacrificial protective cap of the region I want to cut. So I keep the pristine original surface. So it takes a few minutes. And then what I'll do is I'll put a little bit more using the ion beam, and then we'll cut. All right. I'm going to turn on the ion beam. Remember, we have two beams here, so I'm going to turn the other one on. So again, the whole goal of doing the cross-section this way is that because this surface of the material has not experienced any physical damage, right? It wasn't polished or cut or anything. It's just the original surface. I deposited some gold palladium on it, so we should be able to see that as well in the cross-section. That's just to help with conduction. But what's below should be the original glass rod surface. So we're trying to get rid of that question mark in the equation, in the equation that is, how much did we damage with the polishing and grinding? We could still see potassium for a few microns, so we didn't get rid of all of it, but maybe we did get rid of some of it. So let me stop this. I'm going to retract the tube. So here's what I've done. Just that rectangle that you see here. So this region is a little bit protected from the ion beam. And now I'm going to tilt because the ion beam is this beam here at this angle. So I have to start tilting towards it. Okay. And just to remind you, the geometry I'm going for is this one. This one, okay? That's what I'm trying to do right now. The fib at an angle and the SEM here. We're trying to do this. Okay? You can see the curvature of the rod. I wasn't at the highest point. I guess I was a little bit to the side. It's okay. So now, because I'm tilted here, I see with the SEM view, I'm at an angle, but with the fib view, I'm going to be looking at the sample top down. So let's have a quick look. See, now I'm looking here. And see how I'm pausing pretty much rapidly? It's because I'm generating an image based on the fib scanning. But as it is scanning, it is milling the material away. So I don't want to just scan and erode my surface forever, because eventually you get rid of the surface you're trying to analyze. So I just want to position things close to where I want them to be. I'm going to reinsert the tube and deposit a little bit more carbon just on top of the one we've done. All right, do the math real quick. 4, okay. I'm gonna try to go with that. Let me make it a little bigger. See if it works. All right. And deposition works faster with the ion beam. So you just want, when I did the deposition first with the electron beam, that's really just to buy me time, enough time that I can scan a few times like I just did and set up the next step, okay? Now I want to make sure I deposit okay. It looks like I am. So I'm gonna keep going. You can already see where I did a few, not even seconds, but just a few frames with the ion beam. And then I changed the magnification, and now you can see the former magnification and how much it has, impacted the original surface. It started milling things right away. So you got to be careful when you use a focused ion beam, always. Check I'm doing the math right. Should be okay. So again, the tube is flowing a precursor gas that adsorbs at the surface of the sample, and we use the energy of the beam, whether it's the electron beam or the ion beam, to decompose that gas into a volatile part that's being pumped through the system, and it leaves some solid, residue that is what we're trying to deposit. See how the pad is growing nicely here, and then we cut through it perpendicular. So we have to remove everything that's in front. So it's going to take a few minutes. I'm going to try to cut corners. I mean, I would deposit a little more typically, but we don't have forever. So I want to make sure we have enough time to not only cut, but also do the EDS scan afterwards. Let's have a look what we have now. Just do a little more, maybe a minute, and then we'll cut. We're going to say it's enough. I would typically put a little more, but it's okay. Kind of pressed by time, so I don't want to put too much. And I want to have a look at what we've done. Here we go. You can see the pad we've made. Okay. And now we're going to make the cut. So now I'm about to make this one. This large cut. So I need to excavate all of this volume here. And it's really just opening a window so that the SEM can actually see that cross section. So all of this has to go. And to do that, we just really bump up the fib current. So let's see, if I make the shape that I want to make to cut, if I want to go deep enough, and I'm not sure how deep we need to go, that's kind of the guess here. See, it's going to take 23 hours. So of course I need to bump up the current. 2 hours, I have to really bump it up. 13 minutes, that's even too much. 6 minutes, so we'll try that. You see, that's why you really need that protection. Otherwise, you're just going to blast your sample away. Okay. Here we go. Okay, we're going to try to do that cut right here. So you see how it goes fast at the beginning and it's going to slow down as it gets closer to the top. That's because we're making a ramp. We're trying to have this side deeper than here so that the SEM can see this cross section. If I go here and I zoom out, you can start to see where I'm cutting. See, that's the region I'm cutting right now. Hopefully things don't drift too much. You have an idea of what we're doing here. That's the cross-section plane. gotta be careful not to overshoot. Maybe I'll do something like this. All right, let's do something like that. It'll take 5 minutes. Hopefully that's deep enough. When you start getting into the 20 microns, ish depth, that's kind of the bad spot, because it's a little shallow to get a good signal when you mechanically polish things. I mean, you can, depending on the material and all of that, but it's starting to be a little deep for the fib. So usually the cuts we make with the fib are more like in the first 10 microns, but it's just a matter of time. 5 minutes is not the end of the world, but if you wanted to make something deeper, a little wider also the cut, it would take a lot of time. So this is kind of the ugly job of just excavation. We open that window of view for the SCM, and then we're going to try and polish a little bit that face we expose, and then we'll do the EDS on it. What does it look like now? Let's see. Okay. Some interesting patterns here. Again, because it's an insulator, everything's a little tricky. The beam is trying to land exactly on the same spot. So hopefully we can clean it up with the next step. While we're waiting, just like a side comment of on a new machine that we are going to receive in April. Kind of for those samples that are not conductive and where you want to cut something that's a little bit too big, we're getting a cross-section polisher. So it's a sample preparation machine. We're getting one from JOL. Another vendor. Yeah, we're gonna get this one actually that has also the cryo capability. And the idea here is that you can make, so it's not in the SEM, right? It's a tabletop thing, but you can cross-section much bigger sample, and we're talking about things like this. So you see that that's actually a small cut, but yeah, really clean cross sections. It is show. I want to show high. Yeah, there we go. You see 100 microns, so you can make cuts that are millimeter wide, millimeter deep. Really keep a nice surface and everything. And instead of using gallium ions in the focused ion beam SCM like I'm doing right now, it's argon ions, kind of like what I mentioned in the XPS, but it's very soft, so it doesn't make too much damage. And you can really make some large cuts. It's you set the cut to run, you just walk away, and then you come back and you have a really large cut. And then you go to the SCM and you have a really big region to play with. So I think that's something we definitely need to use, in the future. I mean, we'll get it, yeah, a month and a half from now, just know that those things exist too when you are stuck between mechanically polishing and grinding or using a FIB. You have an in-between solution, and that's why we're getting the instrument. All right, so this is what we have right now. It's not too bad. That's the cross-section face. I'm going to save this, but so that everybody kind of understands what we have done, I'm going to try and do something like this. Just rotate a little bit the view. Yes, so that you see what has been done. Okay, so that's the original surface all around. I protected this region, and then we made kind of a ramp to expose that final wall. Okay, we're going to try to do the EDS here. I guess we could already start, but I want to just clean a little bit and go under the carbon pad. Because right now the carbon pad seems like it was useless, of course, but I'm going to cut through it. So I'm going to do that right now. So what we've done is typically called the regular cross-section pattern. It's just trying to open that region. Now I want to do what's called the cleaning cross-section. And that's really polishing of the surface of the face we made. And you want that to go under the pad. It takes a bit of time, so let's see if I can go a bit faster. Something like that. There we go. 5 microns. Time is it? Okay, we have time to do the thing. And hopefully we went deep enough, or at least we can get the signal from deep enough, because it's nice to open that little trench, but we want to be able to place the SEM electron beam inside, I mean, all the way to the bottom of that pit, but we also need to be able to get the X-rays out of it without them being shadowed by the side edges of the trench, that sort of things. So just because I know the positioning of the EDS detector relative to the sample, you will see that I will do the line scan actually on this side and not at the center or the right side, because you usually have some shadowing on the right side of the pit, because the EDS detector is on this side. So when you create X-rays everywhere, those they are mostly reabsorbed here because it's in the shadow of the, I mean, it's blocked in the path to the detector. So that's the reason why I'll do it this way. Let's see what we have now. Okay, let's keep going. 1 minute, and then we'll do the EDS. One good thing about that cross-section polisher I talked about is that, for example, right now, I coated the surface I told you with that gold palladium alloy, just sputter coated for conduction. That's why you have the change in color here. But as soon as I cut through, I exposed the glass, right? So that's not conductive, of course. Whereas if you made a big cut with the other machine I talked about, that sample preparation machine, you can then take the sample and then make a quick coating at the surface of that cross-section, and then you go to the SEM and not have problem. Here, if I wanted this to become more conductive, I'd have to vent the system, coat, and then go back. So it's a lot of time for just such a small region, which it's one advantage of the machine. Now you can really decide where to cut. But if you have a sample that's pretty uniform and you want to have a good idea of a wide region, so it's more representative, that other machine I talked to you about is going to be nice, because you're going to be able to do an analysis over 1 millimeter or more, which is going to be more representative than what I have right now, which is only a 15 microns wide region. All right, so we should be done. Here we go. So we have a nice clean cross section here. Yep. So I'm ready to do my EDS, right? So I'm going to go to the EDS PC, and actually I'm going to call it 100K sample. I'm going to say FIB cross section, this one. Reinsert the detector. I don't need the fib anymore. I'm going to turn it off. Make sure I bring the same settings we used before, 10 kV. See how it's still charging on the cross section again because it's not coded inside, of course. Try to see if you can handle a little bit more current without drifting. Yeah, maybe I'll go a little lower. No, it doesn't have much, so let's do that. Okay, something like that. So if I go back to the PC here and do the drift correction, I think it's going to help. Grab the image and do the line scan. The glass doesn't cut as fast as I was hoping. I mean, I asked for 30 microns, but everything is calibrated for silicon, not silicon oxide. So it doesn't cut as deep, but we should still have like over 10 microns. So hopefully it works well. So I'm going to make the, again, on the left side, make this, click start. Ooh, I see a peak that I like. That's good. It's good to have that. There we go. So let's see where the potassium is. Of course, you have the carbon deposition I made, so it's very rich in carbon at the top. Oh, potassium is here. All right. I think we see some decay here. But 4, maybe 5 microns, 4.5, 5 microns. Yep. All right. So I guess that region that we looked at on the one that was mechanically prepared. I mean, I guess that's interesting because we went to a few spots and some spots didn't show much, but we found, I think I remember 2 spots that showed like 5, 6 microns. So it seems to agree well here. It's always good news when things agree like that. But here, because again, I coded everything around, so you have a little bit better conduction, and I think also, I mean, it's really undisturbed here, so you can start to see that nice decay. Sodium growing up. Yeah. Gallium is the fib. That's what we use for the fib. So you implant a little bit. I mean, it's very little. We don't see much. You see a lot at the top because when we deposited the carbon, I used the fib to deposit. So it also puts a little bit of gallium in there. So I can do a little bit of like a binning, so it looks a little nicer. But yeah. So actually, yeah, if it starts at 1, we go all the way to 7. So yeah, 6 microns seems to be a good figure here.
I think that's the first results we've ever gotten with potassium.
Only took a few years. Well, I guess that's why. I mean, that's why using the several instruments is really the key when you do characterization. If you limit yourself to just the SEM or just the XPS, I mean, you don't get the full picture. I mean, that's great that we have SEMs, fib SEMs, XPS, so we can just have different pieces of the puzzle and then get some pretty good conclusion. I mean, honestly, I'm surprised it works so well on this one. It works really nicely on this one, so that's good to see.
Yeah, and what you mentioned earlier, and I think after they get some of the images and stuff, that they can look at those cross sections that we did, and yeah, the gap, which might indicate some of the crushing or some of the effect from mechanical grinding and polishing,
yeah.
Was on the order of what, 10 to 20 microns,
something like that. Yeah.
Yeah, and it looks like we're seeing less than 10 microns on this sample, so that's a good start, at least in explaining what's happening.
Yeah. Well, I'm glad that worked out. I mean, that shows how this fib works. I think that cross section I did last week, and I mean after the class, and I showed you. I think the silver was deeper. So here it's good that it's only 7 microns. So it's really in the range of depth that the fib is great for, and that worked pretty well. I think the silver on the other sample, that 5% silver potassium, was deeper. So I really had to try and cut deeper. Actually was surprised that we wouldn't see something better on the mechanically prepared cross section for that one sample. Maybe it was really just disturbed, and maybe looking at different spots, maybe there was a region that was that would have shown it, clear. A little bit of a luck, I guess, at that point for that one. Now, that cross-section polisher I mentioned is, I mean, it's made to cross-section, of course, but it's also called polisher because you can also put samples that have been prepared manually, and you put them flat, and you do grazing incidence while the puck rotates. So you have a really nice polish that, again, it's not involving any mechanical grinding or anything. So that could also maybe prepare, or I guess erase those regions that have been mechanically damaged. So I think we'll play with the machine and see the different approaches. What gives you the best result the fastest? I mean, the fib is not super long, but it still took 40-45 minutes. And it was very possible that we could have seen that the potassium was actually much higher, and then we didn't see how deep it went, and then you'd have to make a much deeper cut, and it turns into a monster job, but it was good this time. Okay, I mean, we don't have time to make another cross section, but as I was saying earlier, I think it's the ball's in your hand. If you want to tell me what you want me to do, if you want me to do another sample, whether it's fib cross section, XPS, or the EDS line scan on the mechanically prepared samples, you tell me. If that brings you answers, I know you have, or you are doing some mechanical testing on those samples, right? So if you're trying to relate what we see in EDS to those mechanical results, just feel free to send me an email, and I can just look at a couple of samples for you.
I know one of their big questions, and maybe here in a second we can let them ask questions if they have any. But I know early on one of their big questions was, we were doing the 100% potassium bath, which is what we're looking at now. We did 100% sodium, which in theory shouldn't really do much because sodium's already in the glass, and so it doesn't really, if it exchanges, it doesn't do anything. And then we did silver, the 5% and different concentrations on top of either potassium or sodium. And so I think they were kind of interested in if you have, for example, both silver and potassium, do they both exchange, or does one cut out the other? So we've done a couple samples so far, and I think we're starting to get some data on that. But that might be something that we want to look at, at least in the future.
Okay. Yeah, just let me know. And have you done the mechanical testing, or are you still doing that right now?
We've done all of the mechanical testing. We've looked some at the fracture surfaces. So when the glass breaks, we've got pictures of that. And yeah, so we have all that mechanical data.
Yeah, I mean, if there's something that stands out, yeah, just bring me the rod and I can have a look. Yeah. Any question? Let me see the chat. No. Well, for those who don't know where to find me, I'm in the basement of Aztec. So if you want to stop by and discuss the data, you can also email me, or I'm going to share. I'm going to extract the spectra that we just recorded today, all of those, and share, and also the XPS.
And
Yes, I
so
saw the
Nico's gonna,
the chat from Alexis. Yeah, I'll share everything we've done today. And if something I did today, if I didn't extract the spectrum and you think you need it, yeah, feel free to contact me. And I keep everything, so everything is saved on the hard drive, and we can share that data.
And yeah, so Nico's been sending me the videos and stuff. So when I get it, I'll upload it as quick as possible, the video, and then any data that you get, I'll put it in our share folder. So
okay.
You should have whatever you need to, you can send it to me the way you did last time.
All right. Well, if there's nothing else, then I guess we'll stop here.
All right.
Thank
Thanks,
you for
Nico. That
connecting.
was that was awesome. So
Yeah, it worked.
yeah, I'm glad we finally got something.
Yeah, that's good.
Potassium.
Good. All right. Take care, everyone.
Yeah, thank you.